No, I also got a magnet about one thing that I posted on my story, and it looks like an element of the periodic table.
Yeah.
It's pretty great.
I guess you could say that's pretty elemental.
Wow. Wow.
And its atomic number is 336.
Number of new.
Better call it. What's the atomic? Nice watch.
Whis.
I would assume.
Whis. I'm looking like a maid right now. Whew.
And it has
It's like maid, yeah. Yeah.
I was right over you have done that stuff for years, so you'd be a little nervous there.
I went to sleep
Maybe they would fly back to
I woke up at 6, but 6:20, 6:30, whatever I did, I wake up at 6:30. To work on my British literature study guide. And
I don't know, it's a good course to take.
I call it Kitty Hawk.
Yeah, it is. Because
The flag.
no. But if I get you would even know what I
I'm trying to get what other people do.
If you really think about it, calculus isn't that bad.
What?
If you just really think about it.
Why not?
Calculus isn't that bad. It's just like about limits and stuff.
Did you make the British literature?
Says the one who got the 90 on the test.
I don't know why. I mainly just went through it. I can't really study it for 7 pages.
Oh, I didn't do the more dark one. I was just like, just read it, I know what I'm talking about.
You should bring the restock. It'll be here.
Not for long.
Wait, are you having your mom deliver it?
I'm not gonna leave them in my car. I'm not gonna carry them
Wait,
here.
So you're just gonna let your mom deliver it?
No, I'll go to her car, then bring
Wait,
it
do you have more
Where's your mom's
brownies?
car?
at home.
Okay.
Do you have more brownies?
Mason, what's your email?
Yeah. I'm the combo master. Got him.
Which churches did you use for the Canterbury tales?
You know, you gotta use that,
I just wrote down all the.
you gotta use that Brandon Miller guy.
Oh, you're
And-
doing that.
Like,
I'm not that study guy.
well,
Also,
I wrote down all the characters I remember, like enough about them to say they're.
I mean,
like,
you just basically want like a positive, negative of each type, right?
Yes.
So you want a plowman for a normal guy, for a good normal guy. You want the sailor for the evil normal guy. You want
My dad's the sailor.
Okay, so this morning at Davidson, we're missing
and then there was
Carson Hot Run Style out.
class is starting.
Yes. Wow. You so fucking know this.
What? I was not paying attention.
Exactly.
That's about right.
All right, so what questions do we have? Hey, what? Let's start with questions for one. Let's talk about that. Then we'll go from there. So, volunteer to start us off with 1A. Shortfall, left, right, at a single stage. clearly tell the definition of closed is not equal to the value of the statement. Good, good. One. Mason,
Yeah.
all right?
Yes. Okay, so 1B, true or false? If f is continuous on the open interval 0 to 5, then f is continuous at every point in 0 to 5. And I thought that this was true, and this is due to definition 1.14, and the first example provided under definition 1.14 matches the question.
Good. I agree with you, yes. That's the definition exactly. Good. Anyone see? A volunteer? Josh, would you take it?
Yeah, I would love to. C says if f is continuous on the closed interval bracket 0, 5 bracket, then f is continuous at every point in 0, 5. I said this was false because it is in every point 0, 5, but it also includes x equals 0 and x equals 5.
Yeah, so if it's continuous on a closed interval, then the definition states what? That it has to be continuous at every point interior, but also has to be left continuous at the right endpoint and right continuous at the left endpoint. I didn't keep it. So that's a little tricky. Okay. How about 1D? Who had a razor? Yeah, razor. Thank you.
Letter D. If f is continuous on the interval 2, 4, then f must have a maximum value and a minimum value on 2, 4. Is it possible that it could just be like a straight horizontal line and then you wouldn't have a maximum or a minimum on it?
Well, actually, if you had a straight horizontal line, you would have both maximum and minimum on that. You understand? So, right? So if I draw a graph of a horizontal line, even if I put open circles because it's not included like that, then that's the highest point on the graph and it's the lowest. That's the highest point on the graph and that's the lowest. So I have actually infinite different maximum points and infinite different minimum points on a horizontal line. So that's not the reason it's false. Why is it false?
Are you still asking me? Or is it
Yes.
open-ended?
We'll
Well,
open it up. You can phone a friend if you like.
I mean, that doesn't have to be the explicit counterexample, right? There could be others where it just goes up a little, something like that.
Well, the key word in there is must. It can have a maximum minimum, but it doesn't have to have a maximum minimum. And you're not guaranteed it. That's the idea of the where the if-then things are written. Just because you don't satisfy the if doesn't mean that you can't find an example that satisfies the conclusion. So, well, what is the condition of the extreme value? What's the condition?
It has to be in a closed interval, and this is not a closed interval.
Correct. Without a closed interval, you're not guaranteed of a maximum minimum. You might have a maximum minimum as exhibited here, but this says must, and you're not guaranteed unless it's a closed interval.
How do you not guarantee it? That makes sense. Okay, I'll just take it.
You don't see that, Rizzo? So, for example, if I have something that's not a horizontal line that would clearly otherwise have a maximum in, did you say max in then, or just one? Both a maximum and a minimum. Okay, so for example, this picture is supposed to be open. What was it? What was the interval? I don't know. 2, 4? Okay, so we'll say that's 2 and that's 4. This one clearly has a max. So this is M and this is F of you know. But there's no minimum because you can't hit that point right there. That would be quote the lowest point. But you know, if you say the lowest point is just above that open circle, well, because of the continuity, I can find a point lower that's still not at that open circle. So there is no minimum there.
Okay.
So the fact that if it had been closed, if this had been closed, then I'm guaranteed if it's closed to have a minimum and a maximum. Okay. How about E? 1E. Volunteer? Any volunteer?
If ever people say they're positive, to there must be a value you see at which I can see the other three.
Okay, so if f of negative 3, no, so f of 3 is negative 5. So f of 3 is negative 5. So there's 3, negative 5. What's the other one? It's 9 is negative 2. And what now?
And there must be a value C of which I can see equals.
There must be a value C so that there must be a point at negative 3. It appears to me that would be true, that I would have to go through that point to get there, wouldn't I? Yet the answer is false. I agree. Why is the answer false? How? Okay. So how can I not go through a point between those two? Tell me an example of how I can get from here to there without going through that point. Or maybe, you know, you do lots of things with graphics all over the place, but how can I go? Yes. So maybe my graph does something like this. So what's key? What caused it to not hit that point? What keyword can you put on there? It's discontinuous. They didn't say that it's continuous, so you can't assume that it's continuous.
Dang.
Okay. How about F? Takes volunteers for F. Would you take F for things? Sydney?
True or false if f is continuous everywhere, and if f of negative 2 equals 3, and f of 1 equals 2, then f of x must have a root somewhere in negative 2, 1. And I said this was false.
Okay. Wonder why that is. Okay. Exactly. So let's find it. Exactly. So what were the 2 points they gave us again? Negative 2, 3. And what was the other one? 1, 2. So there's no guarantee that I'm going to go down here. Even though it's continuous, that doesn't, I can easily go continuous from there to there without going across the axis. Okay. As a sign didn't change, I agree. Okay. What about G? Volunteer?
If f is continuous, if f is continuous everywhere, then the f of 0 equals negative 3, f of 4 equals 3, f of x must have a root somewhere 0. Big false.
Actually, no, that one's true. Why is that one true? I'll poll the audience. Why might that one be true? Yes, nice.
Okay, it's true because A, the line is continuous, and B, because one of the points is below the x-axis and the other is above the x-axis. No, sorry, y-axis, and the other is above the y-axis. So therefore, it has to have a root.
Yes, you were right first time x-axis, but yes, you're right. That is actually theorem 1.19 about sign changes. Okay. Okay, good. So H. Carson made it in. Carson, welcome to the show.
Yeah. If f of 0 equals f of 6 equals 0, and f of 2 is greater than 0, then f of x is positive of the entire interval of 0 to 6. And that's false because it only gives you like one place where it's positive, and it could go below the x at any point between 0 and 6. We just don't know, right?
I think so.
Well, let's see. Maybe. Let's see if we can graph that. So what information were we giving again? 0 equals 0, f of 0, and what? F of 2 is greater than 0, so f of 2 is up here somewhere. And the conclusion is then the function is positive for the entire interval 0 to 6. Seems like that should be true. Why is it not true? All right. Give me a guess. It could do something else. Well, what would that something else be? I need to be more specific.
Doesn't have to be.
Yeah, there's a couple of issues. You're right. One issue is maybe they didn't identify all the roots. You know, so maybe it does something like this. Oh no, it didn't have to go there. Sorry, I'll go back. Sorry. Maybe it does this. Another thing is, do they say it's continuous?
Oh crap, that's true.
They didn't say it was continuous, so maybe there's who knows what. I mean, it could be anything. Maybe it's like this, and then there's that, and then maybe there's. There's lots of ways that I can make that happen and not be always positive in that. So it's a couple different issues. Okay, good. What are the questions that y'all come across? How many took home?
Problem 78.
Okay.
Oh yeah, that one.
Who was asking that? I'm sorry, I didn't catch who was asking.
Brittany.
I was stumped on that one.
78. Directions. Let's read the directions first. Explain in practical terms what the extreme value theorem. Oh, that's to 77. Well, then let's just look at 78 for good value. 78. Barnes was 20 inches tall when he was born. And 6'1", we got at 833. Intermediate value theorem to show that there must have been some point in Lorenz's life at which his height in inches was equal to his age in years. Okay. Let's think graphically. So, this is years and age. And this is height in inches. So what's my graph look like? Now there's a point, like say right there, and what that point would be what? How old? 83?
Yeah.
Somewhere way over here is 83. Right on, right on. And how tall is he at 83? So what? How many inches is that?
70.
Okay. So my graph might be like this kind of starts off, we kind of hang out for a while, we're able to go fast, maybe even that age, you might be more like that. So you shrink a little bit as your gravity works on your bones and collapse them. So it's why you get taller in space. Gravity doesn't collapse your bones. What are we trying to show?
It's not ages. It's like
I don't know. It says something about age and years. What if we mapped his age as a line somehow? I don't know. It starts at 0, and then he ends at 83. So that might be like up here. So there's 73. So 83 is going to be way up here. In other words, his age gets higher than 73. He never got past 73, so sometime he had to hit 8 and height at the same time. Age number gets bigger than his maximum height number, so he had to cross someone. Okay. What other questions?
Wait, is there a value we're supposed to find? Okay. That was okay.
No, it says use the immediate variant to show that there must have been something. Let me say find the point. I would not know the exact point unless I know the exact function. Just height. Okay. Other questions? Good on the rest of the section? And that's good. I'm glad. Let's hope. All right. Well, then let's talk about the next section.
No, great.
So the first section, we see the idea of continuity and define what that meant and kind of explore that a little bit. This next section, we're going to take the idea where we said yesterday that the function, linear function, mx plus b, is continuous everywhere on this domain, and we're going to extend that to a bunch of other functions today, which makes calculating limits very simple for most functions. On the first page of this section, page 123, theorem 1.2 gives a whole list of some basic limits rules that allow us to calculate limits for various functions. We already know two limit rules. One is for the linear function and one is for the power function. But this allows us to put those types of functions together in groups and come up with more complicated functions and still be able to calculate the limit. So we had two specific types of functions yesterday. That's specific rules. What I mean by specific, I'm going to insert specific functions. And we covered two yesterday, and this is more later. We saw that the limit x approaches c of mx plus b is equal to c. M times c plus b. And then we saw that the limit x approaches c of a times x to the k. So we do a times c to the k. So this is yesterday. This is linear. This is power. We're going to see some more today, but we're also going to cover some what I'm going to call general function rules. So these will be ways of combining our specific functions that we learn about in various ways to build more complicated functions. So the first one is a very simple one. We call it the multiple rule. And it simply says that the limit x goes to c of k times f of x equals k times the limit x approaches c of x. I could prove that real quickly. I guess we probably should. First of all, on this, make sure you understand what it's saying to you. This function here inside this limit is a transformation of the function f of x. Thinking back to pre-calculus, what kind of transformation? If you multiply k times f of x, forget limits, go back to pre-calculus. How is this a transformation? What does it do to the function f of x as a transformation?
It stretches it.
Which way?
Well, it depends on if it's positive or negative.
Okay, you're right. And which direction in terms of horizontal or vertical?
Oh. Well, we're talking about stretch.
You can stretch this way, or you can stretch this way. Which way are you stretching?
I didn't know you could stretch
When
horizontally.
you plug in an X, what do you get out?
Maybe I'm
Of course
just
you
dumb
can
right
stretch horizontally. Of course you can stretch horizontally. That's part of the transformation. You can change your horizontal scale, and you can change your vertical scale. That's
Are you talking
transformation.
about like if it's a fraction or
This
something?
this one is multiplying a y value times k, so it's clearly stretching the y value.
Vertical?
What this is saying is this function that is a stretch of the original function at the limit will simply be a stretch of that limit value. So it makes sense to me that if I'm going to take a function, if I've got some function f of x, I multiply it by k, that's going to stretch that function taller. So this is k times f of x. Then it seems to me that if I'm looking at a particular value c, and this is L, then this at C, that value there is going to be K times L. That makes sense to me. That's what this says. We're going to prove that now. Okay. So quick proof. So again, this is just a stretch, vertical stretch of the y values, and so the limit is just going to get stretched as well. That kind of makes sense. Okay, so we're going to assume that limit x goes to c of f of x equals some number L. That's like a given number. And we want to try to prove this statement here. So to prove a limit statement, how do we start it? I was just doing the last test. Yeah, let's let epsilon be greater than 0. Let epsilon be greater than 0. Good start. Now, normally at this juncture, you would pick your delta. But before I do that this time, I've got to leverage the knowledge that this function has a limit. In fact, to try to help us understand, I'm going to go back up here to my assumptions, and we're going to let h of x equal k times f of x. So I'm actually giving this stretched function a name. Okay. So I'm trying to prove that the limit of h of x is what this says right there. Are you with me? Now, before I can choose my delta, I'm trying to prove this one. So before I can choose my delta for this one, I'm going to need to know something about what's going on with this one. So I'm going to start with saying, by definition, there exists, let's back up. Hang on, we'll get it figured out here. Before I write this, I need one more piece of information. So I need to say, this means, you'll see why this is important here in a minute. This means epsilon divided by absolute value of k is greater than 0. Do you understand why the epsilon over k, absolute value of k is positive? If epsilon is positive and absolute value of k is already positive, then the division has to be positive. Mm-hmm. Okay. Now by definition, so here we get to the definition. I'm focusing on this one for a moment. By definition, there exists a delta, we'll call it delta f for the f function. And I'll do a delta h here in a minute. There exists a delta f that's positive, such that if 0 is less than absolute value of x minus c is less than delta f, then absolute value of f of x minus L is less than epsilon over absolute value. I haven't proved anything yet, folks. All I've done is set it up so I can prove it. Let's review this bit right here. One more time. Maybe I should add a little color to help identify. Black is going to be the main part of the proof. But what I'm doing here is this business right in here is just leveraging the fact right here. I need that information. I'm referencing the fact that function f has a limit, and that limit is L. And therefore, the definition says the meaning of that statement right there from our definition is all of this. It says for any epsilon greater than 0, this has to occur. Well, I've got an epsilon, but I created a new. So this thing right here is kind of like my epsilon for my f. It's just another epsilon that's also positive. So it has to work for any epsilon. So I have an epsilon, well, it has to work for this one. That has to also work for this epsilon. This new shrunk value, if you will. So all I'm doing is I'm shrinking this given epsilon to a smaller epsilon, and it still has to work. Now, once I've established that and I've got a delta f, then it's fairly easy. We'll let's choose. Use the word choose to match stuff. Choose delta h to equal delta f. Let's assume x is located such that 0 is less than absolute value of x minus c is less than delta h. So we're starting the proof of the h function now. We're going to use this knowledge in here. Delta h is equal to delta f. We now know that this is less than delta f, and that gives me this statement. So let's see what we have. This gives us, and we're going to start off with trying to prove h of x has a limit that we think. So we're going to do h of x minus, and we think the limit is k times the limit of f, k times the limit of f. So we think it's k times L. So let's see if we can prove that it is in fact k times L. L is the limit of f, and we want to show that the limit of h is k times L. Mm-hmm. So, all that?
Is that 1?
Here. Oh yeah, no, that's absolute value. I'm sorry. So absolute value. What is h of x defined as up there?
K f of x.
That's f of x. Good. Minus k times L. Well, we're almost there now, folks.
I'm so close. Oh my gosh, I see it.
Here. What do we need to do next?
Factor out a k.
You gotta get that spec.
K needs to come out, and we get f of x minus L. But because delta H and delta F are one and the same, delta H and delta F are one and the same, then this thing, f of x minus L absolute value, what did we just say? It's less than So this is less than absolute value of k times epsilon over absolute value of k, which equals epsilon. So now we've done it. We've leveraged the fact that the function f had a L by getting it, saying, well, look, if I just got to get a h, this function h under epsilon, I can squeeze my original function even tighter to get it to work out. And that's what we did. Okay, so that's an easy one. How can I use that? For example, that multiple thing kind of comes into play. It's multiple rule right here. You see this multiple m, that's kind of like your multiple k. So that's not a big deal theorem, but it's an easy one. Another one is called the sum rule, and this will really expand our range. So limit function c of function f of x plus function g of x is equal to the limit function c of function f of x plus the limit x of function c of function g. So we don't say the word distributed because we're not really distributing here. Distributed is the multiplication across addition, but the limit notation appears like it's been distributed. So it's saying that if you take the limit of the sum of two things, you can take the limit of each thing individually and then add after the fact, which is sort of like distributed with multiplication.
I can dig it.
Proof for that is not too bad. Let's see how much time there. Well, the proof, I'm going to just read it. It's in the book, so we'll let you read that one. It's on page 129. It's not too difficult. It involves, the trick is the same type of game right here, except we will have two functions, and the idea is you're going to add the two functions together. So when you start with epsilon greater than 0, you're going to start off with epsilon be greater than 0. And if you've got, let's suppose you've got f of x goes to L as x goes to C. And g of x goes to M, call it. We're going to use that knowledge that both of these have their own limits and start with the epsilon, but then we're going to use the knowledge of these two functions and do something like this, but instead of epsilon over absolute value of k, you're now going to be using epsilon over 2. And from epsilon over 2, then you're going to get a delta for f, and the delta will be I'm not going to go all the details in, but there'll be a delta f and a delta g at work. Not a proof, whatever that means, all this rest of the stuff. And then once you have your delta f and your delta g that work, then your delta for your h, so you're going to let h be the sum. So if h of x equals the sum of f plus g, then your delta h is going to be equal to the minimum of delta f and delta g. And when you get the minimum working, then you're getting both of them working at the same time. And then it's a fairly simple process. To go through this same type of game, you'll have a little more involved, but it works out that you'll be adding epsilon over 2 plus epsilon over 2, which gives you epsilon. So it's not too bad. The rest of these get even more complicated. So that's the sum rule. The difference rule works the same way. The product rule works just like you would think. So the sum and difference, I'm just going to call this the sum and difference rule. Plus minus, plus minus. Okay, so the product rule works just like you would think. And then x approaches c function f of x times function g of x equals the product of the two individual limits. minus. And the other two are similar. You've got a quotient rule, which again, to me, quotient products are kind of one and the same. The only difference is on the quotient, you got to be careful that the denominator is not 0. So I'm just going to put, it's in the book, it's similar as the product, similar to the product, but g of x in the denominator cannot be 0. G of so, got a composition rule too. Limit x approaches c of g of x equals f of x approaches c. So all of those are nice functions, allow us to do some bigger things. So a few quick examples of that, and then we move on to some other things. Let's see. So a quick example. Here's one. So we're going to limit x approaches 4 of 2x to the third power minus 6x plus 2. And so without taking out a calculator, doing a graph, or doing a table, I can evaluate this fairly simply by doing the sum rule. So this is going to be the limit x approaches 4 of 2x cubed minus, so this is the sum, I'm doing the sum and difference rule. Minus limit x approaches 4 of 6x plus limit x approaches 4 of 2. That first one looks a lot like a power rule to me. Does that look like a power rule to you?
Yes.
So if I use power rule, and that one's going to give me 2 times 4 cubed. And then over here, I've got a linear, that's linear 6x plus 0, and this is linear. If n was 0, then that's also linear. So I'll use my linear rule now. And that says I can just, it's continuous, so I can just plug in that 4 there. It's 6 times 4 plus 2. So the whole point is that this function I can evaluate by simply plugging in the 4, because each component in this function is in fact continuous. So whatever that is, 128 minus 24 is right. I did a lot of sleep last night, so I'm not sure which one. My brain's kind of, and I didn't have my coffee today, so my brain's kind of like, whoa.
Mm-hmm.
That right number?
I got you.
Okay. That's right, good. So this it demonstrates a theorem, another theorem that they wrote in the book, and that theorem says that all algebraic functions, so on page 124, continuity of all algebraic functions. Hey,
I already used one. That is. Gerald Walker said, like around with silver Ford Focus.
Mm-hmm.
I know James Walker.
All right, thanks. All right, there you go. Coming after me.
What is happening?
I didn't see this. Our campus sheriff just popped his head in, and I thought I was being arrested.
Not yet.
Not today. Maybe tomorrow. So,
Social police.
what I was saying was, or trying to say before I got arrested, was Arrested Development or something. Is on page 124 is a theorem that says all algebraic functions are continuous across their domains. That's a broad statement. That function right here is an algebraic function because it involves pluses and minuses and division and products. So that theorem kind of makes it real simple to evaluate limits for most functions. That's real nice. That theorem comes from all of those theorems listed over there. If you put all those together, the ones we just did, and the one we proved, and so on, if you put all those together in one big bundle, you get theorem 1.22 on page 124, which is, hey, put it all together, and you can say any algebraic function is continuous on its domain, so all you got to do is plug in to find the limit. If the limit is, if that value is in the domain, if it's in the domain, then you can plug it in. Well, that's real convenient. One other thing that the combination function allows us to do, real simply, the limit x approaches 2 of x minus 3 to the 5th power. Well, this is, to me, I see as a combination function. We have an inside function x minus 3 and an outside function 5. So that's like a f of g of x kind of thing. So like the combination over there, the bottom row. So that means I could do this as the outside function 5th power of the limit x approaches 2 of x minus 3. Yes. Notice that the limit now is inside the 5th power. As long as it's continuous at the appropriate locations, in this problem I made up, it is. We're not having any issues with continuity on this type of function. So with this, I now have simply -1 raised to the 5th power, which is.
Oh, that's really good. Oh my.
So it simplifies some of your calculating limits. You definitely don't, for most things, don't need tables and graphs. You can do it very quickly algebraically. Next up is sometimes functions are algebraic, but they're a little different. They have some domain issues. So I'm going to go middle board here, I guess. That involves a little bit of algebra that you've done in pre-calculus. It's not that difficult, but I want to emphasize a point to you before you start just doing it. So let me ask this question. There's an expression, call it a function, whatever. Can you simplify that?
Mm-hmm.
You think the answer is?
What did he say?
What would this simplify to if you had to simplify that expression?
1 over x minus 2.
1 over x minus 2. Does everyone see this?
Yes.
You can factor it. The denominator is x plus 2 over x plus 2 times x minus 2. And then you learned in pre-calculus algebra that you can just cancel this out like that, right? Then you get 1 over x minus 2. So now my question is, are we sure that this is a true statement? Let's take a poll. Poll the audience. All who say that what I've written is exactly true, raise your hand. Okay, the way I've asked the question, it's got to be false. So yeah, it's false. Why is this not exactly true?
Why isn't it? That's a fair question.
Isn't it because in the first part you can't have -2 as x because 4 minus 4 is 0, but in the last part you can have -2 as x?
Exactly right. Who was that? I'm sorry, couldn't see who was talking.
Someone.
Sammy, thank you, Sammy. And can you, Amanda, can you turn towards Sammy? Just I can't really see Sammy. Plus, I can't see when their mouths are moving. Anyways, this would be true if I said x not equal to -2. So now the point is that this function has a more restricted domain than that function. So we have to include the extra restriction to make these two things actually equivalent. Are you clear on that? Well, that comes into play. So if I ask you to find the limit x goes to -2 of x plus 2 over x squared minus 4, then by what we just looked at, okay, so let's pause for a moment, keep going. Okay, so what we just said a moment ago, if you got this algebraic function, all these things going on, and then the one theorem that kind of puts it all together, we said, as long as it's in the domain, you can just plug in the function value and you get your limit. Okay, so what happens if you just plug in on this one right here? Plug in a -2, what happens?
Yes,
Is it undefined?
Yes, sort of undefined. So if I apply the algebraic property that we just mentioned, so that's whatever theorem number that is, we'll call it continuity of algebraic functions. We'll call it CAF. Continuity of algebraic functions. If we ignore the domain issue, which that is a big issue, then what happens is you get 0 over 0, which we call that in calculus not undefined. It might be undefined. It might be another value. So we'll call it a different word. We call it indeterminate.
It's like my future.
Now, I know in middle school you were taught never to divide by 0, and we're not actually going to divide by 0. But it turns out that if you're dividing by 0 into a numerator of 0, sometimes we can work things out when we're talking limits. So the limit here is called indeterminate, and so we take a different plan. And we're going to spend the whole next section, not today, in a lot more detail on indeterminate. But here's a simple example of how to handle one type of indeterminate. We will alternatively, instead of doing that, we'll say, well, if we agree that we're not going to let x is not going to be, what do we say, -2? So x is not equal to -2, and I can say that this statement is equal to the statement limit x approaches -2 of 1 over x minus 2. Do we agree with that? So I'm using some new notation that you probably haven't seen before. What I've written is an attempt to cover what we just discussed up here. So I'm trying two different paths. It's like I tried one thing. I said let's just try the continuity of algebraic functions and plug in. And oops, I ran into this 0 divided by 0. I'm a little sketchy on that, so I don't want to do that. I'm going to back up and try a different plan. So now I'm going to go a different direction, and I'm going to simplify my algebraic function by canceling, like I've done many times before. But I'm going to make a note to myself that in canceling, as Sammy said, I can't let x be -2. So I'm going to include that as a note that this equality holds only if I make sure that I don't let x be -2. Okay, well, when I'm doing the limit as x approaches -2, right here, the limit as x approaches -2, are we going to let x be equal to -2? No, what does the definition of limit say?
As it approaches the value.
Yeah, we've got the distance. Remember that punctured interval whole thing? Go back to the very beginning. Punctured interval. At C, we didn't ever talk about what happened at C. It was only close to C. So when we're talking limits, we're talking a punctured interval, so we're never going to let it be -2. So we're taking care of the concept of limit is going to take care of that issue for us. And now I'm going to say, well, that's taken care of. I'm not going to actually hit -2. I'm going to get real close. This is an algebraic function, so I'm going to try the continuity of algebraic functions. So I'm going to try the continuity of algebraic functions theorem again. How would you get? Continuity of algebraic function says if it's within the domain, I can simply plug into the function to get the limit. So plug into this function, this new function, get a limit. What do you get? 1 over -4, don't you?
Yeah.
Which is equal to -1/4. So, in fact, 0 divided by 0 is really just -1/4.
Oh my gosh. Oh my gosh. Please.
You can't do that.
Oh, that'll be fine. It's actually -1/4. This time. Now, next time it might be 17. Question, Joe? Yeah. You're right. Okay. Good question. It's like, wait a minute. You said I can't let x be -2. You're right. But then I plug in. It's because I'm plugging in. I'm not. That's a good question. I'm not. On the limit, we're not really going to hit the -2 mark. But the theorem says that if it's the function I'm dealing with is continuous, then the limit value that's not actually hit the mark is equivalent to at the mark. So in this new function here, like up here, -2 is okay in that function. It's just not okay in the original big function. Now here, -2 can't be used in the original big function because we ended up indeterminate. In order to strike out that factor that caused the problem, then I had to up here assume that x is not -2. So x not equal to -2 allows me to change from that function to this function. But then this equal sign is not dealing with that anymore. It's dealing with this. So this comment allowed this equal sign from here down to here. Once I'm to here, now I can apply this because that's a different thing. I'm answering your question. Good question. Seems like you're kind of robbing Peter to pay Paul or something, but that's okay. Okay. So I think you should try one more. How much time we got? 4 minutes? Man, I didn't even get halfway through this section. Okay, there's a lot in this section. You should try one. Maybe like this. Practice. Let's see if I can do it.
This is where derivatives come from. This is where
Have a hand up somewhere? Yes. Please?
Yeah. Is that type of thing where the derivatives come from?
Yes. Exactly. We're gonna, when we get to derivatives in the next chapter, we will have a function that will create an indeterminate form when we try to apply the limit. Remember the business we had at the beginning of all of this, when we found the speed of Galileo's bowling ball that he was talking? Remember that game? Well, speed involves a derivative, and we were taking a limit. We didn't tell you that at the time. We were doing it numerically in a table. We went through limits to do derivatives, as Lee said shortly, and that will involve an indeterminate form, and then we will come up with a speed or something. Rachel had his hand up too? Yes.
With that example that you gave on the right, with the x plus 2 over x squared minus 4, could you just use the quotient rule for that? Is it possible?
Well, yeah, the quotient rule is effectively incorporated. Good question. The quotient rule is effectively incorporated into the continuity of algebraic functions. So in other words, honestly, the reason I got 0 divided by 0 here is I applied the quotient rule. I plugged in -2 into the numerator, got a 0. Plugged in -2 to the denominator, got 0. So I used the quotient rule to get there. I referenced the continuity of algebraic functions because in my mind, the continuity of algebraic functions encompasses all of those rules. If you roll all of them together, you get the bigger rule called continuity of algebraic functions. That answer your question, Reza?
Yes. Thank you.
Okay. Real quickly before we head out the weekend and all is everyone try number 38 on page 135. Just real quick on your paper. See if you can do 38. That's the all of what we just talked about. Your homework will go further than that. There's a lot more in this section that we've covered. You'll have to do some reading on that. Try that real quick.
Go. Yo, this is foul. Go. Please tell me I got it right. Yes. Got him.
But if we get indeterminate, if you try to just plug in initially, top and bottom using the quotient rule, as Rachel said, you get 0 divided by 0, which is indeterminate. But if you factor and cancel in the way we just talked about, then you should get -10 as your answer. So this time, 0 divided by 0 is not undefined, and it's not -1/4, it's -10. The question, Reza?
When it comes to doing this, do we have to do the top thingy with the indefinite part, or can we just go ahead and simplify it? Indeterminate.
Yeah, you can go ahead if you want. That's fine. You don't want to try to simplify it. Yes.
Okay.
It will be good to identify if it's indeterminate later. We will see a time when there are theorems that apply to indeterminate forms that don't apply to other units. So I always take a point to show that what I'm dealing with is indeterminate before I do anything else with it. In this situation, it's not critical. You're right. But later, I think it will become more critical. So I would encourage you to get in the habit, but for now, if you don't, that's okay.
All right.
Right? All right, well, I'll try to post some homework for you for section 2 here shortly. I'll see y'all Monday. Make sure you read that whole section. There's a lot more in it. We'll try to wrap it up on Monday. How old? Some of them are, some are not. Some of them didn't do it. Well, others will stick. Others are sick. Honestly, most I would ask you to do class. Others, some rules aren't too bad. Once you pass some rules, once you have quite a bit. I usually read it. That's getting beyond our scope. I mean,
He said it
our
was
class
a
has a calculus. We need to do something. But it's not a high level. So that's good question. If I were you, I would make sure I could do something like fairly simple. At least as compared to the others. It's not simple, that's how you see it. Trust me, it's a lot more simple than the others.
I already talked with him and they said that it would count as my basic chemistry.
Yeah, that's it.
So I'm.
But if you went ahead and did that before in general chemistry,
I shared
if you did it before doing general chemistry, you can compare an extra semester.
Yeah.
Actually, it's extra 2 semesters.
I don't even know.
I did the practice test.
But I know I don't understand something.
I was stuck on that density one.
I understand.
I don't know why.
Fasting.
I'm gonna need some help on it later. It was question
Not
16, I think it was. It was the only question about density.
Proof I said was simplistic.
I got
You were
something.
a long time ago. A long time ago.
Are you heading to the game? Okay.
That means that's only equal one. You remember that? And I was like, okay. Times 2 doesn't equal 4.
Yeah, like, yeah.
No, I'm asking, 'cause that's
I am sleep deprived, I'm
that's the
cranky,
whole concept.
I'm frustrated.